The topic of rotation. I just about choked on myself. This is a challenging topic, I think. It is helpful if you relate it to things you already know, which are things we studied earlier in the year. So I'm going to go through a fairly lengthy review handout. I'll scroll through it slowly. So you could stop it at any point. But we'll go through each page a little more. In this handout, I'm looking at formulas and doing several sample torque problems. There's one, there's two, and there's the third one, and then two rotational problems. I don't know why that paper is crooked, so I don't think I really drew it that crooked. Rotational problem 1, and this is a whole page. And I changed some of the parameters. And then rotational problem 2, which deals with conservation of angular momentum. All right, back up to the top. I think a big idea behind this whole topic is keeping the idea that anything with rotational motion has a linear analog, meaning a linear quantity that relates to the rotational quantity, a linear equivalent. So I've shown those here. The equivalent for force is torque. The equivalent for mass is rotational inertia. Equivalent for acceleration is angular acceleration. Remember, acceleration is meters per second per second. Angular acceleration is radians, or parts of a circle, per second per second. Velocity and angular velocity, displacement and angular displacement, momentum and angular momentum, which is symbolized by capital L. Some of the formulas we know: acceleration is force over mass, angular acceleration is torque over moment of inertia. Momentum is equal to m times v, angular momentum is I times omega, or wonky w. The impulse momentum equation, torque times time, that should be delta t. I should fix that. In fact, I will fix that. Torque times delta time, nice, is equal to I times delta w. So kinetic energy and rotational kinetic energy. These things in green are how you convert from linear measurements to angular measurements. Since radians is unitless, radians per second squared. I think I told my classes per second squared. I hope you remember it's unitless. So if you multiply that by the radius, which is in meters, you would get meters per second and meters per second squared. There are only two real formulas that are unique to rotation, and one is with torque, which is Fd sine theta, or F perpendicular times the distance. We did talk a little bit about moment arm or lever arm distance, although I tend not to calculate that. And then the moment of inertia itself, or rotational inertia, is equal to mr squared or something similar. So for example, this would be for a hoop. 1/2 mr squared would be for a solid disk. 2/5 mr squared for a solid sphere. Mr squared would be actually for a point source. That's the only one you should really probably know, is that mr squared is for a point source mass, is the moment of inertia for that. So much for all the formulas, but what about the ideas? Well, the rotational inertia of an object depends on A, the amount of mass, B, the radius of the object. So it could either be the length if you're talking about a rod, or the radius if you're talking about a sphere or a hoop or a disk. And then finally, and very importantly, it's mass distribution. So more mass, more rotational inertia. That makes sense because that would make it harder to change the rate of rotation. Bigger radius, also more rotational inertia. Essentially, that means the mass is spread um, more of it's further away. And then the shape affects it because when the mass on average is further from the center, you have more rotational inertia. That's why a hoop with all its mass on the outside, and a bicycle wheel is similar to a hoop, has more rotational inertia than a solid disk or a sphere of the same radius and the same mass. So you should be able to predict a couple things. One is the order at which rolling objects will finish when rolling down a ramp. So this depends only on mass distribution because all objects of the same shape, such as all solid spheres, all solid disks, all hoops, if they're uniform density, have the same ratio of torque to inertia. So on the same incline, that is. And I don't know why that word ratio is not there. Okay, I'm going to do another thing here. Ratio. And I'm going to make that be green. Nope. White. White. Text color. Green. Oh. Okay. At any rate, so all solid spheres would have the same acceleration on the same on the same incline. You should also know that a point source is placed on a rotating object. Its rotational inertia is mr squared. Talked about that earlier. Its angular momentum is m times v times r, where the radius is, this case, is where it was placed from the center. You could prove that by showing that this multiplied by omega, which gives you angular momentum, and omega becomes v divided by r, essentially becomes mvr. Sample torque problem 1. You've got a hamster. I know that's a wonderful drawing at 75 centimeters on a uniform meter stick. So in this particular case, it's got a mass m. To maintain equilibrium, where could a force of mg over 2 be applied, and in what direction would the force be applied perpendicular to the meter stick? So key thing here is recognizing that torques have to be balanced, so counterclockwise torque would equal clockwise torque. And so the force of mg over 2 could be applied at 0 centimeters directed downward, or 100 centimeters directed upward. Why? Well, the hamster is causing a clockwise torque, so we need the extra force to cause a counterclockwise torque. That counterclockwise torque needs to be applied twice as far away from the fulcrum as the clockwise torque caused by the hamster, because the magnitude of force is only half as much. The hamster's mass is m, so the gravitational force would be mg. Torque problem number 2 is a uniform plank of weight 400 newtons and a length of 4 meters sits with 1 meter over the edge of a cliff. What's the farthest distance out on the plank that Mrs. Osmet, mass 60 kilograms, could stand without causing the plank to tip? Well, first of all, I drew a picture. So there's my cliff here, the 4 meter long plank. I show the 400 Newton weight acting at the center because it said it was a uniform plank, meaning the mass is distributed evenly throughout, and it's hanging over by 1 meter. So its fulcrum would be at the 3 meter point. Now, if Mrs. Osment wasn't there, this wouldn't tip because the center of mass is over a support base. However, as she walks further and further out, the center of mass of the person plank system moves further and further out also. And when the clockwise torque ends up equaling or becoming greater than this counterclockwise torque, then she's going to flip over. So figured out her weight is 600 newtons. Sorry about that. And then I chose a natural fulcrum, which I showed you with x. So torque counterclockwise equals torque clockwise. So we've got counterclockwise torque is 400 newtons of force times a 1 meter distance from the fulcrum. So I use 3 minus 2 meters on the plank. and that equals 600 newtons times whatever distance she could walk out. So it says she could walk out up to 2/3 of a meter and be safe. Probably not feeling very comfortable about that. So she could walk up to 3.67 meters, actually 3.66 meters from the left end. Torque example number 3, this is a two-body problem, meaning there's two forces upward. So you've got a 100 Newton swing, it's 2 meters long, hangs from two ropes, one on each end. Find the tension in the rope. If there's a pit bull, again, sorry about the drawing, mass 20 kilograms that's sitting 0.5 meters from the left end. First thing I did was find the weight of the pit bull, so its force. Second thing I did, actually I think this was the first, is draw a picture. I know that torque is equal to perpendicular force times distance. I should know that counterclockwise torque equals clockwise torque for an object in rotational equilibrium. Force up equals force down for an object in translational equilibrium. So setting that equation with torques equal, I have one counterclockwise torque caused by the rope on the right side, and that needs to equal the two clockwise torques caused by the pit bull and the weight of the plank. That gets me that the force of the rope on the right side is 100 newtons up. Now, I could solve for the force of the left rope by moving my fulcrum to the right edge of this, and do similar equations again. All my measurements, however, would be from the right side to where the forces are, including the force of the left rope. Or I could get kind of smart and realize that in translational equilibrium, the force up is equal to the force down. 200 plus 100 is 300 newtons. So now coming down here, that allows me to figure out that the force up on the left rope is 200 newtons. That should make sense because the dog is closer to the left side than the right side, so the left rope would have to be pulling up harder to maintain equilibrium than the right rope would. This is rotational problem number 1. So I've got a solid disk, moment of inertia mr squared over 2, and I think the AP would normally give that to you. Mass m, radius of r, rolling down a hill of distance L, and angle theta. If the disk starts from rest, what's its speed v at the bottom of the hill if it rolls down? Oh, I already said that. Answer in variables and fundamental constants only. Hey, fundamental constants, what is that? Like g, or maybe k for a spring constant, something like that. That's it. So think energy here. Initial energy equals final energy, but it's not just gravitational equals kinetic. It's that gravitational potential energy equals kinetic energy plus rotational kinetic energy. So in this case, I know that the gravitational potential energy is mgh, but I don't know h. I can solve that with trig and say that that height that it's rolling from is L sine theta. I know 1/2 mv squared is my kinetic energy, and 1/2 I omega squared is my rotational kinetic energy. But I need to substitute things in for that because I've got way too many variables. So I was told that a solid disk's rotational inertia is mr squared over 2, and you should know that an angular velocity is equal to a linear velocity divided by radius. So therefore, angular velocity squared is equal to v squared over r squared. Doing that simplifies things, and I can cancel out mass. These r squareds cancel out, and so I end up getting 4/3 GL sine theta. If I repeat this problem for a solid sphere, similar things happen, except the ratios are different. And that's because the moment of inertia, or rotational inertia for a solid sphere, is 2/5 mr squared. I don't think the AP would have you do quite this much math. They might, if they gave you some of these fundamental formulas, but I think they would ask you to compare which one would get down first if they gave you these two. Let's say if they gave you that a sphere's inertia was 2/5 mr squared and a disk's inertia was mr squared over 2. So you should recognize that the object with the lower coefficient has less inertia, and therefore it'll be able to roll down faster and get down there first. So, and that's because on average the mass is closer to the center of the sphere. This last one is a rotational problem that involves clay being dropped onto a potter's wheel. Solid disk of mass m, radius capital R. The blob of clay is mass m over 4, and it's dropped vertically at r over 2 from the center. Sticks to the wheel. The inertia of the wheel is given as mr squared over 2. You should know that the clay would have an inertia of its mass times just r squared, r being where it is dropped, which happens to be r over 2. So this is an angular momentum problem. AP might ask you some things about whether it slows down or stays the same speed under certain circumstances. You do not need to use radians per second. It gave us this as RPMs, or revolutions per minute. That's also an angular velocity, albeit not a standard one. So if I know my formula for angular momentum, then what I can do is figure out angular momentum before equals angular momentum afterwards. I get before is 30 mr squared. This is pretty complicated. So the clay is m over 4 is its mass, r over 2 is its distance, but r over 2 has to be squared. The whole quantity r over 2 has to be squared. And those two things come up to mr squared over 16. And then the moment of inertia for the disk stays the same as it was before. So overall, I have a greater inertia at the end, therefore I'm going to have a lower speed, which is about 53.3 RPM. And now I have a question of, if the rate of rotation is increased until the clay just begins to slide off, at the instant just before it does, draw a free body diagram, assuming that the clay was at this location. So normal force and gravitational force are equal. Friction is actually acting to keep it in. So remember, with objects in a circular path, the net force would point in. It's going at a constant speed. Technically, in this case, if it was slowing down at the instant the clay hit, that would be a little different as well. So that would be a little more complicated. Not undoable, but I don't have a picture here to help you with that. CS is the question, elastic or not. That was way too simple a question. I don't think the AP would do that. They might ask you if something's an elastic collision if the clay were to bounce up off of it, which would be a little harder to figure out. The idea is elastic collisions have mechanical energy conserved. That does not ever happen when objects stick together, and that's why this is an easy question. The last part was saying assume that the artist drops another piece of clay that firmly sticks on top of the first one. So right here, it's twice as thick. At what rate of rotation will the heavier clay slide off compared to before? Greater, less, the same? That would be the same. Why? Because the part of clay sticking to the potter's wheel is sticking due to friction. And the coefficient of friction only depends on the material that's interacting, and that's still going to be the clay in the potter's wheel. So if the blob was dropped on top, you'd have twice the mass, which is twice the normal force, but also twice the friction, because again, the coefficient of friction would be the same. So there's a lot going on in these problems. I think the key thing is to think about general concepts and conservation laws like momentum. I think with torque, you want to think about location of where forces are acting and whether or not they're perpendicular to a rotation axis. And again, I think that will help.